Hello students, today we are going to discuss about N-type and P-type semiconductors. We have learned about semiconductors. We know that semiconductors can be classified into two main types, that is intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors are nothing but semiconductor which is in its purest form. And when we are adding some impurity to a intrinsic semiconductor to improve its conductivity, then it will become extrinsic semiconductor. So the process of adding impurity to a semiconductor, that is doping, and the material which we are adding is called as a dopant. So these many things we know, and already we have discussed that extrinsic semiconductors are again classified into two types, that is N-type and P-type. Here in this video we are going to discuss in detail about N-type semiconductor and P-type semiconductor. As we have already discussed, if we are taking a lattice structure of a silicon atom, we know that it will be having 4 electrons in its outermost shell, and when it becomes a crystalline structure, it will be having many silicon atoms, right, like this, and it will be going on, right. So in order to improve the efficiency of a semiconductor, what we'll be doing? We'll be adding doping. How we can add a dopant? It's like either we can add a donor impurity or we can add a acceptor impurity. Both the things we have already discussed. Now let's say I am adding a impurity which is of a pentavalency, which means it will be having 5 electrons in its outermost shell. So right now we are having 4 electrons in its outermost shell. Now I am adding some impurity and improving its conductivity by adding a pentavalent impurity. Okay, so right now how many electrons will be revolving in its outermost shell? It will be 5. 4 should be there for taking part in covalent bonding, and 1 will be a free electron, right? So when in room temperature itself, this free electron can be grabbed by the next silicon atom and thereby the next. So what is happening here? What is getting increased? An extra electron is there to take part in bonding, right? So in this manner what we are doing is we are improving the conductivity by adding a pentavalent impurity, right? So by adding a pentavalent impurity, what we will be getting? We will be getting a free electron, right? By getting a free electron, what we are increasing? We are increasing the conductivity, right? Okay. Fine, these two things we have already learned, and it's a very simple thing. So we got a free electron as well as a improved conductivity. So now if we are considering the whole crystalline structure, there what is happening in all together is there the majority charge carriers will become what? Majority charge carriers in a N-type semiconductor will be what? N-type semiconductor is electron, which is carrying a negative charge, right? Electron. So this is all about N-type semiconductor. Now when we are considering about extrinsic P-type, when we are considering about P-type semiconductor, there also I am going to take the same silicon crystalline structure where we know we will be having a silicon atom which is having 4 free electrons, and when it becomes a crystalline structure, we will be having many silicon atoms. I am considering only 3. As I have told before, so we will be considering only 3 silicon atoms which is there in a crystalline structure. So in order, over here what we will be doing? We will be adding a impurity to improve its conductivity. How we will be adding? We can add a tetravalent, which means the valency of the impurity which will be adding will be 3, which means 3 electrons will be revolving around the last orbit. Okay, so here if we notice, we can understand that here the majority charge carriers, because right now it is 3 and I am adding some other impurity, and there what is happening? The neighboring atoms is having 4 free electrons, and the place or the atom which I have replaced with another impurity will be having only 3 free electrons, which means here the majority charge carriers will become positive, because this place, the 4th place, will becoming empty, Right now we have added a tetravalent impurity. So in this atom's outermost shell we are having only 3 electrons and the fourth place will become empty, which means here, or this empty place, we will be calling it as holes. So when we are talking about a p-type semiconductor, the majority charge carriers will be holes, which will be having a positive charge. So when it comes to n-type, the majority charge carriers will be electrons. When it comes to a p-type, the majority charge carriers will be holes. So in other words, we can write here in n-type, number of electrons will be greater than number of holes, and when it comes to p-type, number of holes will be greater than number of electrons. This is all about n-type and p-type semiconductor. Okay, so I'll repeat, we'll recap it once what all things we have learned, so it will be easy for you to remember. What is our n-type semiconductor? N-type semiconductor is nothing but where the majority charge carriers are electron. How we will be getting the majority charge carriers are electron? When we are doping it with a pentavalent impurity. When it comes to p-type, the majority charge carriers will be positive, and how we will be acquiring that stage? By adding a tetravalent impurity. So here we will be adding 5, here we will be adding 3.